All right, well, let's see if we can answer the question. I'm going to show you something that might help. The difference quotient is something we do in advanced functions. We name it to begin. It's one of those things where you call it by name, but then we use it a whole ton, but we don't use the name of it. And we don't require you to know it by name. Some things we do, some things we don't. Like difference of squares is something that you should probably know by name, difference of cubes. But the difference quotient, I don't know. But what if I show you this picture? So what do we have? We have 2 points. 1 point is occurring at A, 1 point is occurring at X. And as I bring X towards A, what's happening and what happens there? Does that help? Anybody else think about what the difference quotient is? Emma, what do you think it is? So can you tell me what it actually is? Yeah, and we're actually missing an important part there, but nice. Very good. So now everybody's like, yeah, right. Of course, we all know that. We call that the difference quotient, if you recall, or slope of the tangent, we call it. We actually also call it the derivative. So we're talking about the derivative today. You've kind of been doing it, but we're going to do it. We're going to introduce a new way of doing it as well today. So it's got a few different names, and the derivative is a big idea, and it's the essential building blocks of calculus. So this is really where we're getting started on this stuff. But like I said, you've been doing a little bit of it already in advanced functions, and using this formula to calculate derivatives or find slopes of tangents, that sort of thing. Okay, now I want to show you another demo. What's this? Click. Look carefully at what's changed. I'll go back. I know, it looks like nothing, doesn't it? You're like, sir, give me a break. You're changing it? Okay, so this is our new one. This is our calculus version. The old version was the functions version. This is a calculus version. And watch what's going to happen. Think about what's happening in relation to what was happening before. Okay, and here's my challenge. Now you can do this with an elbow partner, or you can try to do it yourself and then compare it to somebody. I want you to try to rewrite the difference quotient with the new demo. I'll leave the picture there, and you've probably written it down, but okay, give it a try. Even if it's wrong, folks, try. You can scratch it out. This is a worthwhile activity. Talk to somebody. It helps to talk. Bounce an idea off somebody. Turn to talk. Somebody that you're close to. What do you think? I'll talk to you. You know what's wrong. So what do you think is wrong with this? Here, I'm going to give you a hint. Think about where this formula originally came from. Grade 9. Spread those 2 points back apart so you can see a little bit better. Okay, we're really on to something here. We're close. Can you share with us the first part that you came up with that we had a discussion about, that just the limit part? Okay, and stop right there. Think about that. Like, what do you think about it? Ka told me he just observed that's what was happening in the graph, in that demo. So if we have a point A, we used to have that point A before, right? It was A and X. Now it's A and A plus H. So H is the horizontal distance between these 2 points, right? It's shown there, but that's where this point comes from. I'm adding some value to the first value, and that's the horizontal distance between my 2 points that I'm finding the slope. Remember, this is called the secant? When it cuts through a curve, a straight line that cuts through a curve in 2 places is called a secant. You can find the slope of a secant. That gives you the average rate of change. Remember that? But then the problem is when 1 point is on top of the other point, you get 0 over 0. Now we know that's called indeterminate. And we had this old way of finding the slope of a tangent, which probably seemed good enough. You're like, why are we complicating it? Why are we doing it in a new way? The old way worked perfectly fine. But anyway, we're going to do it anyway. So this x value is a plus h. And as I bring these 2 points closer together, what's happening? The difference between the h value that separates the 2 is approaching 0, right? That's what's separating the 2 points. So this is the limit statement that we want. The limit as h approaches 0. Now, what's the rest of it? So it would be this, y2 minus y1 over x2 minus x1. This is really good because if you ever get stuck, now you're probably going to use this formula enough, and it's similar enough to our old one that you won't forget it. But it's nice to know where a formula comes from in case you ever need to rebuild it. Maybe next year you need to, when you're in university or college or something like that, right? Like maybe it's not this year, maybe you'll remember it this year, but in the future. So go back to y2, y1. So what are my y2s and y1s? Well, y2 is the function value at the x value of this, like the second x value. So if this is my second x value, a plus h, I get f at a plus h minus f at a. So that's just y2 minus y1. And a lot of people had that around the room. You had that top part. And then it's a plus h minus a. And what does that work out to? Just h. So this is the limit as h approaches 0 of f at a plus h minus, and we actually usually use x. Well, we go back and forth between x and a, but often you'll see this written with x in there instead of a. But our demo had a, so we used a. Okay, so that's our new formula. It's so important. We're going to put a box around it. It has several different names that we refer to it. So it's called the derivative, as I said. And we note it as a notational thing, y with a tick mark or an apostrophe, and that is called y prime. So we use the word prime. Y prime is the derivative of y, or f prime x, or f prime. We also call it this, which is weird. And this is this is how you say it, dy by dx. And we'll start using that notation a little bit just to get used to it. That's a very common calculus notation. What do you think that one comes from? Kind of. There's something else to it. There's actually a different form of the formula that you might have seen in grade 9. And I think I used it at least once last semester. Yeah, I remember. Just talking about it. Delta y, delta x, change in y, change in x, right? So then instead of writing the triangle, it became a D. And then instead of saying delta y, it just became dy. So you've probably heard this before. Two separate mathematicians invented calculus. One of them was somebody that everybody's heard of, Isaac Newton. And in some of the science that he was doing, some of the math that he was doing related to his experiments, it wasn't working out. And so he invented limits in calculus, or maybe not invented, but he improved upon it in such a way that it was like, became a whole new thing. And he did it separately from another person called Leibniz. Leibniz is known as a philosopher and a scientist for sure, and a mathematician. And he's nowhere. Has anybody ever heard of that name before? Yeah? And nobody else? Where have you heard?
Me?
Yeah.
Whenever you look at like calculus, it says it was created by
Okay. So
Isaac Newton.
just in thinking about calculus and that kind of stuff. So he was, like, as I said, he was also a philosopher. So he's actually known as a famous philosopher, but he's not as well known. Nobody in here knew him. Everybody in here knew Newton. Very interesting. However, his version of calculus was way more eloquent. Turns out Newton's was like a notational disaster. It was really messy to use, whereas Leibniz's was much more eloquent and easy to read and easy to teach and easy to learn. So that's the notation that we tend to use is Leibniz. And so you'll see that in the textbook it actually says Leibniz notation and always just says dy by dx. That's not the only part of Leibniz notation that we use. And it doesn't matter. You don't obviously need to know any of this. It's just kind of interesting. Leibniz is, I think, thought of as one of the most brilliant minds maybe who's ever existed. People who have studied him think that he was like beyond intelligent. He may not have been in as many academic circles as Newton, and that's why he's not as well known and wasn't as well accomplished. I know he is well accomplished, but anyway, that's that. Okay, so let's go on and let's use it. Let's use our new formula and see how it works. The steps involved are different. Algebraically, they will feel different. Otherwise, the idea is very much the same. and you recognize this question, find the slope of the tangent to the curve. So it might say find the derivative. Find the slope of the tangent. Find the instantaneous rate of change, right? Like all those mean the same thing. And just as a quick little reminder, what's this over here? Actually, I will use blue. This means f at 6 equals 12. X equals 6y. There's no y, but we sometimes do interchange f at x and y, right? Y equals 12. So those are, I know that's pretty basic, but those are the details that part of the question is telling us. Just remember that. It will kind of be important to be able to think about that. So what are we going to do? We're going to do f prime at x equals the limit as h approaches 0. And this is just our function. And because I used x over here, I'm going to use x in my formula, x plus h minus f at x all over h. Is everybody okay so far? Then we're going to write f prime at 6 equals the limit as h approaches 0 of f at 6 plus h. So the h is still there. You're not subbing in for h. You're subbing in for x. Whoops, f at 6. Often what I would do is, if I had to, is do the f at 6 part off to the side like we did the old in functions. Like we already know what f at 6 is. It's 12. So often I would do that off to the side and just put that in. But we're just kind of showing some extra steps, right, for the lesson. Is everybody okay with that? And really remember, like, what is h? H is the horizontal distance between the two values that we are doing. So it's the limit, as like all this depends on limits. The limit as h approaches 0. If h was 0, it would be indeterminate because we'd have point over point. We'd be finding the slope of that, and that won't work. So we have to take the limit as h approaches 0. H is the distance between my 2 points, and it's getting smaller and smaller and smaller and smaller. Everybody okay? Okay, now we're just going to, now we sort of sub in on top. So what is f at 6 plus h? Well, f is that. So I sub, like function notation, right? Whatever's in this part, for function notation, whatever's in there goes in for all the x's in the original function. So that's what we're going to do. So it's x squared, but what is x? X is 6 plus h squared minus 4. And don't forget that it's that there's 2 x's, 6 plus h. And if there were more x's, I would sub in everywhere for x. And then what's f at 6? It's 12, so minus 12 over h. So that's different from what we've seen before, where we've got that binomial squared part in there, and we've subbed the 6 plus h in. But that's kind of what we always do when we're using this type of formula, so you'll get used to that. Okay, so we're going to expand. So what's 6 plus h all squared is 36 plus 12h plus h squared minus 24 minus 4h minus 12 all over h. I don't want to forget that. We're not used to expanding binomials in reverse order. You can change that and make it x plus 6 if you like. That's absolutely fine. But just because of the way the formula is, and we tend to leave the formula like that, h is what we're adding. So you'll probably see me usually do it like that, but it really doesn't. Like, it could be h plus 6 is fine. Or if you just leave it as 6 plus h squared, but then when you expand it in your head, do it the other way. I mean, it's fine. Now something really important happens here. What's 36 minus 24 minus 12? 0. This must occur. Now, this is a polynomial type, so the other types are going to look a little bit different, but like the idea is the same, that in every type, there's a thing that has to happen so that this works out. If we were doing a bigger question, like a cubic or something like that, and the math would be a little bit harder, you'd be expanding a cubic, right? So it'd be like 6 plus h all cubed. That expansion's a little bit trickier. You're more likely to make a mistake. For polynomials, that's the constants still have to add to 0. You'll see why in a moment. I'll point it out. But if it didn't happen, just like in functions, there's your check that you've made a mistake just in your algebra. That has to work out that way. Okay? If it didn't, you've made a mistake above. It's not like, oh, maybe this one doesn't work out. No. It has to work out. Okay? So equals limit as h approaches 0. And as I said, that, and that are gone. And then anything else? Nope. 12h minus 4h, we're still going to have that. So I'm going to have h squared plus 8h all over h. Does that look right? You see what's going to happen now? What are we going to do now? Yeah. And why are we going to do that? Right. So if I still had the constant, the top wouldn't be common factorable. And it wouldn't work out. Don't force it. Don't get to that step and be like, I know what's supposed to happen next. I know the h's are supposed to divide to 1. But I've got this constant that's not letting me do that. I'll force it and just make it happen anyway. No, like go back and find your mistake, right, if it's a test. And then I can sub-zero in. We've got it. Any questions? Pretty straightforward. Old idea, new outfit. Okay, let's try another one. This one's slightly different. Different? It's the same function. But we're going to find the general derivative. So what does that mean? It means not at a particular point. This is often what we're doing. This is where we're going in this course. And it's nice to do this if you have to find the derivative at a bunch of different points. So if we want a formula for the slope of the tangent, that I could, so if I have a curve, and maybe it's a distance over time, so the slope is speed, and I want to find a bunch of speeds along my trip, then I would want to find the formula for the slope of the tangent, and then I could just plug my times in and find the instantaneous speed at those times, right? So if you're only doing it at one, like the last question, maybe you do it that way. But if you're doing it a bunch of times, it's probably easier to do it this way, and that's what we're going to do, is we're going to then use it to find 3 different instantaneous rates of change. Okay? So how do we do that? So what we have here, our point, just like we were sort of talking about before, is x comma f at x. So f prime at x is the limit as h approaches 0 of f at x plus h minus f at x over h. What is f at x plus h? What did we just talk about? Function notation. You take whatever's in those brackets and you sub it in for every x in the function. So it's x plus h all squared minus 4 times x plus h. And what is f at x? That's our function. So folks, you have to subtract and make sure this is in brackets. F at x, which is another way to just think about, well, the original function, which is x squared minus 4x. Does that make sense? Maybe you want to watch for a second, right? This is this. F at x equals that. That's just the function. Those are the same thing. Okay, and then this was that same function, but evaluated at x plus h. Do quite a bit of function notation in grade 11, and then we use it, but maybe not as much in grade 12. Now we expand and simplify. What's x? I'll challenge you to try it yourself, actually. So what's x plus h all squared? I mean, honestly, you could write out both. It's not x squared plus h squared. Oh my gosh, if you do that, oh my gosh, you're going to give me a heart attack, right? It's not x squared plus h squared. When you square binomial, you get 3 terms. So make sure you do that correctly. If you have to do it the long way, fine, but ideally you can just jump to it. This is what I got. And so something, again, important happened here. If you think about the last example we did, and I talked about how the constants have to be gone, they were the only terms that didn't have an h in them. As long as every term has an h in it, you can common factor out the h, which is what we want. So what are all the ones that don't have an h in them should be adding to 0. Let's see if that happens. I've got x squared minus x squared. Good. I've got negative 4x plus 4x. That's good. Every other term has an h in it. So I'm good. So I've got h squared minus 4h plus 2xh. So I'm going to factor out an h. H times h plus 2x minus 4 over h. Gone. Any questions so far? H plus 2x minus 4. And then what do I do?
7, 0 for h.
Yep. So I get 0 plus 2x minus 4. You don't need to show that step. Equals 2x minus 4. Voila. Formula for the tangent, slope of the tangent to that original curve. And what we call f prime x or dy by dx or whatever, depending on the notation. Usually depends on the notation the question is given to you. If it's given as f, you use f prime. If it's given as y, sometimes you use y prime or sometimes you use dy by dx. Any questions? Okay, so 2x minus 4, f prime of x was 2x minus 4. So f prime at 4 is 2 times 4 minus 4. 8 minus 4, so 4. F prime at 0 is 2 times 0 minus 4. So we're just whipping through this, right? It shows you how much nicer it is. 2 times 2 minus 4, which is 0. A lot nicer if you have to do it 3 times to bother doing it that way. Otherwise, if I had done the other one all 3 times, it would look like that original expression, right? It would be a lot longer. Any questions? All right, we got a couple more. We might only get to one of them. One of them is a rational function, and one of them is a is the radical function. So if we don't get to them, I'll do it and post it. Just so you can see an example of it. We'll see what we can get through. All right, so I want you to try this, getting started on this one on your own. So dy by dx equals f at x plus h minus f at x over h. Whoops. Don't forget, don't do what I did. The limit as h approaches 0, that's an important part of formula. Okay, so I want you to try to sub in to this example and see how far you can get. That's what I have so far. What technique are we going to use for this one? Yeah, we're going to do conjugate one. Okay, so there we go. So one thing I want to make note of is, what's going on here? There we go. Be careful of this. You want it in brackets because you're going to multiply through the whole thing, right? But that top ended up being pretty straightforward, but I got this mess on the bottom beside the h. Oh my gosh, don't multiply through. We want the h factored out. That's what we're doing next anyway, right? So that's handy. And what happens? I get x minus x and 4 minus 4. If I forgot the brackets, technically I wouldn't get that. I get 4 plus 4, right? So then it wouldn't work out. So I get h over h times that whole thing. Of 1 over the square root of x plus h plus 4 plus the square root of x plus 4. Now just watch maybe for a minute. Something interesting kind of happens here. Limit as h approaches 0 of 1. No, sorry, I want to get rid of that. I'm subbing 0 in. So I get 1 over the square root of x plus 0 plus 4 plus the square root of x plus 4. So what is this? How can I rewrite this? Yeah. I've got 2 of them. 2 of the same thing, so I've got 2 of them. Okay? And that's our final. Our final form for that one, for the general derivative. And then I think it asks us to solve it at a couple of places. I'll let you try that. It's pretty straightforward. There's a couple of different ways we can do this, but so the problem with this notation is there's nowhere to put in, like function notation is so nice because like f at this, there isn't that for this. There's a few different ways to do it, but I'm just going to say at x equals -3 just below. Okay, so equals 1 over 2 square root of -3 plus 4. So that's 1 over 2 times the square root of 1, which is 1/2. And so that's the square root of 9, which is 3, times 2, which is 6. So there you go. That part, hopefully, isn't going to be the hard part for us. Any questions? There's our practice. I do have one more example, but I think I'm going to stop. I would encourage you to try it if you want, and then you can check your answer against Classroom. I'll put it up after. We got 5 minutes in case you have any questions or anything else that you want to go over. Find the general derivative and the slope of the tangent when x equals 2, 4. So find the general derivative and then sub it at 2.